So previously we had a look at designing in terms of mechanical design, and it was primarily based on, I suppose, the mechanical requirements of the part. So if we take the rivet in the Titanic, for example, the steel rivet was more malleable than the iron rivet, and therefore it would have been a better selection. However, a huge part of modern manufacturing is trying to limit the amount of environmental impact of your product. Now, that means that you have to have a look at the geometry, the joining methods, where it was made, how it was transported, and what is often one of the biggest factors, the material itself that you're choosing. Because the material that you choose defines where that original item came from. So is it timber? Is it sustainable timber? Um, is it aluminium, for example, which could be recycled from your base material? Or if it's not aluminium that's recycled, can it be recycled at the end of its life, which it can. So aluminium is a relatively environmentally friendly metal in that regard. Um, but it also has a lot to do in terms of how it's processed, how the part is manufactured, where it's assembled, its use, and its end of life. So when people talk about examining environmental impact using that kind of broader look, it's called life cycle analysis. So we're going to have a look at what it means to do to carry out a life cycle analysis. We're going to use something very simple in terms of a coffee cup and different types of them, compare those. And later on, you're going to complete a workshop that will allow you to use a very simple plugin in SolidWorks to allow you to get data based on, okay, if I choose one material for this part, or if I swapped it to another, how much environmental impact it could be reduced or how it could be lessened. If I manufacture it in Asia as opposed to Europe, where it's going to be sold, and any finishing treatments we're going to put in it as well. So at the start, and this is really important, we're going to have a look at coffee cups because they're a very simple product that we all use, we're all familiar with, we should be familiar with most of the materials that are in them as well. This can be used for very, very simple objects like coffee cups, but where it's actually the most useful is when you consider far more complicated products such as cars, because cars and planes emit the vast majority of their environmental damage during their use period, not in their make period. We'll talk about that in a couple of seconds. So again, to give this a broad kind of area when you look at where the damage to the environment is coming from, we can look at it in terms of production. So what it takes to make the product, where the energy is coming from, how we transport the materials, emissions and other pollutants from manufacturing. We can have a look at the use, how use of the product impacts humans and the environment. So again, the use of a coffee cup has virtually no impact on the environment. Bar cleaning it with some hot water and some soap, it doesn't really have a huge amount of emissions in its use cycle. Um, However, if you compare that to a car, the vast majority of its total environmental impact actually comes from its use, not its production, and not its post-use in terms of recycling. And then post-use, how disposal of the product impacts the environment. So certain products are very recyclable. If we take drinks cans, for example, aluminium, widely recyclable, widely used in terms of recycling processes, and are actually valuable as a recycled product because we can bring aluminium back to a very good quality metal from the recycling process. Whereas paper, for example, while it can be recycled, the paper that you get out of the recycling process is never as good as your base stock. So it'll often be used for cardboard boxing or packaging or something like that. It doesn't require nice, clean, crisp white paper. And so down the bottom then we see that your total environmental impact equals the cost of production, your cost of use, and the cost of post-use. And again, we're lucky using SolidWorks in this way, which you'll see in the workshop, in that it actually calculates all of this for you. You just enter some data such as where it was produced, what material you're using, what machining process are you going to use, and it will give you a very, very slick, very well polished report automatically for each part at the end. Your job is to interpret the data it gives you and to make sensible decisions based on that data. So once again, today we're going to focus primarily on concepts associated with life cycle analysis. When you do the workshop, it'll be focused very much on where to get data, how to compare parts, and how to make an informed decision at the end of that process. When considering environmental impact, it's important that we're relatively specific because a lot of people say something is good for the environment or bad for the environment. And again, like our material selection problem, that means nothing. If something is bad, how much worse is it than its competing product? If it's better, how much better is it? If it's going to cost twice as much and only save impact on the environment by 2%, is it worth doing that? Will enough of them sell to even recoup? So all of these factors, be it marketing, logistics, economics, they all play a factor in this. But when we're looking explicitly at the impact on the environment, we are looking at emissions in terms of global warming and air pollution. So examples of those, as we know from global warming, we're seeing consistent trends in terms of rising temperatures. This is causing rising sea levels, coastal erosion, flooding in many different countries. And even in Ireland, if you look at the amount of times Cork City has been flooded in the last decade compared to the 100 years before that, the frequency is incredibly high. So it is important as well when considering global warming that it's not about one warm day or one cold day. So anecdotally, you could say, oh, but in 2012, we had one of the coldest years on record. Yes, we had one of them. But if you were to average it across 10 years, you'd find that the average temperature is significantly up. Another problem with global warming that is perhaps more complicated is that we are also way more likely to get extreme weather events. So because we put more energy into the weather system, in our country especially, it will swing left and right an awful lot more. So what I mean is we'll get occasional storms that are very, very cold, blizzards, that will go well below the temperatures we should be expecting in winter. But equally in our summer, we're going to see temperature spikes we never saw before. We're going to see lower rainfall leading to droughts that will last longer than they ever have before. Now, this change will be gradual. You'll have to look over the course of 20 or 30 years, but its impact is undeniable when you look at the broader data sets that are being used. Now, air pollution is different to global warming. Air pollution is specific to the quality of air that you're breathing in your locality. And that's why you see congestion charges in London, for example, where they don't want internal combustion engines operating those areas because too many engines around too many people will create significant problems in terms of the amount of NOx, which is nitrogen oxides in the air, or particulates, which are just small physical pieces of carbon in the air. So if you've ever seen a diesel car accelerate away from a traffic light, you might see a puff of black smoke. Chances are that car was pre-2012. So that was when Euro 4 emission standards were brought in. We now are operating on Euro 6 emission standards, and we've added a lot of stuff to stop cars polluting air quality locally. Natural resource use, in terms of deforestation, biodiversity loss. So if you talk about, let's say, sustainable forests, it's kind of a trick term because if you look at a fully evergreen forest, maybe Scots pine, which is the most predominant type of tree we grow in this country, where it has about a 15 to 20 year cycle where it's grown, harvested, reset, grows again. That isn't actually as environmentally friendly as it sounds, because if you walk into an evergreen forest that are all grown at the same height, you'll find that the carpet of the forest, the floor of the forest, is almost completely devoid of life because it blocks all the sunlight coming in because all the trees are the same height, which they wouldn't be in a natural forest, but also because they're all the exact same type of plant in a tree. It stops other plants from growing around it. Now, this leads to biodiversity loss, which means you'll get very small amounts of plant life or alternative animal life in that environment. Again, compared to a traditional forest. And then global warming is again linked to this because the more carbon that we send into our system, it's a carbon cycle. So at the moment, we're adding way, way more than we're taking out. Trees actually help to take carbon out of the environment and essentially sequester them into solid wood. And that's an interesting term that's used a lot at the moment in terms of environmental science and sustainability, carbon sequestration. What that means, very simply, is when we grab carbon that's in the air and we turn it through a chemical means back into a solid block. Again, think of the carbon that's used in your pencil. And then we simply sequester that, we bury it. It's not very chemically reactive, it won't have any environmental impacts, but we're drawing it out of the air and we're storing it back in the ground. It's almost like the exact opposite of what we do with fossil fuels, which are very, very carbon dense. We didn't burn them, converting all that carbon into gas as it exists in the air. So we want to reverse that process. Bill Gates is actually currently funding a project, I think to the tune of over $1 billion, where it creates big industrial chemical plants that their sole purpose is to scrub carbon out of the air and sequester them in the ground. We'll talk about that an awful lot more next semester in terms of taxation policies and impact on health but it is something to be aware. So if you see these articles in the news, you should be looking into them. In terms of pollution, biodiversity loss, we've covered. Degradation of natural environment is actually linked very heavily to this. So you'll note that when I said rising sea levels, I mentioned a couple of times coastal erosion. So I grew up on a small farm that is by the sea. We've lost about 20 foot in terms of our low-lying land to coastal erosion since I was born. Now, 20 foot, if you spread that, or I should use metrics here, let's call that 8 meters. 8 meters spread across a coastline that's a couple of miles long means you're losing a couple of acres. And for any of you from an agricultural background, you know that this can be very, very serious in terms of impact. Ireland, being an island nation, is particularly susceptible to this type of damage. But other countries are going to suffer even more. So, for example, the Netherlands have very, very low average altitudes in terms of their land mass. A significant amount of the country is actually under the sea level, and they will have serious challenges in the years ahead. So those are terms that you should be familiar with. If you're not familiar with any of those terms, I'd ask you now to pause this lecture, go away, watch a couple of YouTube videos, do some reading and catch up, and then start the lecture again. So this comparison is drawing exclusively from coffee mugs. Again, the use of analogies when you're teaching can be very, very useful. So this is quite a complicated concept. So by using relatively simple examples, it's to aid your initial understanding. It's not to suggest that this field is that simple. It most certainly is not. But I'm going to use comparisons to highlight the changes in terms of geometry, material selection, and performance on your decisions when you make a coffee cup or when you buy a coffee cup. So a big part of technology education is actually educating consumers, because while we are not all going to be engineers after they complete that subject at second level, all of them will be consumers, and we are all consumers. So we have a huge impact on our local environment based on what we decide to buy and based on what we decide to use. So very interesting one here, styrofoam cup, which by the way is banned in Europe under legislation, but if any of you have been to America, you'll notice that styrofoam cups are very, very popular there as takeaway containers. They are very, very popular because they're incredibly cheap to manufacture, cheaper than paper cups. But they have certain environmental problems come end of life. Now, one of the major issues with them is that when they break up, and I'm sure you've seen this in packaging, you get those awful little styrofoam beads that just float around the place everywhere. Now, left outside, they will eventually end up in water. They will make their way through our water systems to the ocean, and that is leading to a massive problem called microplastics. There's a lot of very good documentaries on microplastics, plastic impacts, how it's in most of our food chains at the moment. And a recent study from a very, very well-respected academic group out of Harvard suggested that out of the 20 samples of human waste that they used, they found elements of microplastics in every single one of those traces, which means that it is incredibly likely that everyone listening to this lecture has actually ingested a considerable amount of microplastics just in your day-to-day consumptions of food. Now, in certain doses, that's not really that dangerous. However, as the concentrations increase, it will lead to kidney failure, liver problems. It's a very, very unfortunate impact of our modern way of living on our health. But right now, we're going to come back and we're going to look at purely the amount of energy used per cup. Now, this is actually a pretty simple concept straight off the bat. So consider energy, if you can imagine even a flame burning. So we have to put a certain amount of energy in order to make any product. Now, just by changing the material, we massively change how much energy we have to put into a product to make it. So just for a second here, I'm not going to pause or anything like that. I just want you to take 20 seconds to think about this. The styrofoam cup seems to be taking an incredibly small amount of energy. We've talked about its drawbacks in terms of end of life, but in terms of energy in its production phase, it's very, very low compared to, let's say, even a glass coffee mug. So I'd like you to think about why that would be the case. What's different about the two as you hold them in your hand? What's different as you experience them using them as products? And you can see it's even lower than a paper cup there. So if you haven't used a styrofoam cup, if you're only familiar with paper cups, again, you can do essentially the same comparison between the paper cup and the glass coffee mug. The ultimate factors that govern that difference are going to be the same. So take 30 seconds to think about that. You can leave display, I'll give a gap, and then we'll come back and we'll explore that comparison. Okay, so let's have a look. So again, I want you to think, first of all, glass coffee mug, which is our middle one there, and styrofoam cup. Before we go any further, the energy here is in kilojoules. So that's your unit. Kilojoules is your energy, and then we've divided it by cup. So the first thing you should note, if you're holding a styrofoam cup compared to a glass coffee mug, the first thing you've probably noticed is mass or weight. Now, the glass coffee mug is going to be much, much, much heavier, maybe 10 to 20 times heavier, maybe more than your styrofoam cup. Again, depending on geometry, depending on what type of glass you're using, and also its performance. So big, big difference there. And that's actually where most of the energy difference comes from. Because in order to shape styrofoam, and you don't do the following, but if you choose to burn styrofoam, you'll notice that it almost completely disappears and leaves only a tiny trace of solid material afterwards. It usually actually puffs up into the air and floats away. That's because styrofoam, it's polystyrene expanded with air, so it's whipped up like candy floss. And ultimately, it's about 98% air. So in terms of the amount of energy needed to shape it, it's very, very low energy. If you wanted to heat up a butter knife, you could slice it through a styrofoam cup very, very easily because it has an incredibly low density. Whereas glass coffee mugs typically have to be solid glass and they have to be quite thick. Because glass is quite a brittle material, we need to make it quite thick so that it can survive the day-to-day impacts that it would in its typical use. Now, another one, and this is very, very simple, but also you can see it in the name there, it's based on the material type you're using for the mug. So when you use glass, there has to be a reason for using a material that is ultimately much more expensive and also much harder to produce and also much more energy intensive to produce. Now, look up the very, very top then, you've got your ceramic coffee mug. And ceramics are very, very similar in terms of glass, but they require even higher temperatures. So while a ceramic mug might weigh roughly the same as a glass mug, typically the energy required to go into a ceramic coffee mug is much, much higher, purely down to the heat that you have to heat ceramic to in order to get it to flow like a liquid and essentially shape it or sinter it in order to create a coffee mug. So why does a styrofoam cup require so little energy to produce? Because it is ultimately of 95 to 98% air. It's down to energy density because there's very little material in it. So if the glass mug that we've talked about previously requires so much more energy than our styrofoam cup, well then why would we want to use that? How is that possibly an environmentally responsible thing to choose as a consumer or as a designer? And it comes down to very, very simply the principles that we were all taught in primary school. Reduce, reuse, recycle. And reuse is one of the most powerful things we can do in terms of reducing our environmental impact. So to calculate and compare the average cost of use for disposable cups versus reusables, we have to answer one key question. How many disposables are equal to the continued use of one recyclable alternative? Now, let's put that more simply. How many styrofoam cups would I have to use once and throw away before I would equal the environmental impact of my glass coffee mug? So until I get to that number, I've actually made a worse decision. It's called a break-even point. So if, for example, I am incredibly clumsy and incredibly forgetful and I'm buying a new glass coffee mug a week, it's highly unlikely, unless I'm an absolute raging caffeine addict, that I am going to be actually making a better decision. If I keep losing it, if I keep buying new glass ones and breaking them and throwing them away, I'm making a worse decision. I should have used a paper cup or a styrofoam cup. But if I'm a responsible consumer and if I'm reusing that cup, and ultimately, if we take the paper cup here, if I use it enough and I drink about 40 cups of coffee instead of using paper cups, it's now a positive environmental impact. Every cup after that, I'm saving the environment another impact. So the quick answer, this number ranges from 6 to 127. Again, depending on what you're comparing to. So if you're comparing the styrofoam cup to the most environmentally friendly reusable plastic cups, it's about 6. If you're comparing the styrofoam cup to the most energy intensive ceramic coffee mugs, it's going to be about 130 cups. So assuming you're drinking 1 cup a day, that ceramic coffee cup mug is going to have to be in use for over a third of a year before it's going to be the better environmental decision. So everything we considered previously is more to do with the cost of production. But now let's consider the cost of use for our average coffee cup. So the picture there on the left is your typical paper coffee cup that you would have gotten out of the Scholars or out of the shop, wherever you get your takeaway coffee or tea. Now, the one to the right, here's an interesting one. You might still see some of these floating around. This was an initiative launched 2 years ago by UL, and it has the green reusable keep cups, they're called. And they are, because they're green, they must be environmentally friendly. And I hope sarcasm comes across in digital lectures, because that was supposed to be sarcasm. The problem with those cups is that they are not environmentally friendly. The green parts you're seeing there are silicone. Now, silicone is very, very good from a performance point of view because it's a good insulator, but also it has a pleasant feel as a grip and also as a mouthpiece. But then the white part of it is actually made from PLA plastic, which is called polylactic acid plastics. Now, that cup was advertised as environmentally friendly and recyclable. Neither of those two things are essentially true. Because of the PLA plastic used, if any of you still have one of these cups, you'll notice that the inside stains terribly. And when you scrub it with any kind of abrasive, you'll actually remove some of the PLA plastic. So it's not advisable to use an abrasive cleaner on it. So when it becomes discolored, it's less likely to be used again. Because it is PLA plastic, it also, while technically recyclable, is not recycled in this country, which means we'd have to ship it to China. Most of the recycling that happens in Asian countries, and China is now actually rejecting most of the recycling from westernized countries because the quality of the materials was too low, i.e. we don't clean our stuff when we recycle it, and we don't have good contamination procedures here for it. So ultimately what you ended up was all the green parts, which are again supposed to signify environmental friendliness, are completely non-recyclable and actually have a considerable impact. And the piece that they are claiming to be environmentally responsible in terms of the main body is also a poor material choice based on its performance and a poor material choice based on its end of life. So that is one problem. Often what is marketed as environmentally friendly is not. That's why we have to look at it from an empirical point of view. When I say an empirical point of view, all that means is we have to have data, numbers to compare it to. Because if you just feel or you just believe something is better, that is not the same as a fact. And this is a big problem in modern media. I feel something, therefore that is true, is not a reasonable way to live our lives. It's not a reasonable way to be active citizens. Just because you feel something or you perceive something does not mean it might be true. So we have to have data to base on our assumptions. Now, let's consider our cost of use. The cost of use actually for the paper cup is very, very low because ultimately it's only used once and thrown away. All the cost in the paper cup is really when you're making it. Whereas the cost of use for a reusable cup, we should be factoring in something like cleaning costs, whether that is a hot or a cold wash, something like that. Now, one way of doing that would be, okay, how many times are we going to wash it over the course of a year? If we're going to wash it one time or a week over the course of a year, which is low, we can very easily just say, okay, that's a dishwasher load, and we can figure out the average energy consumption for any dishwasher. And we can have that available, that data available to us and use that. So there's a huge amount of data out there. It's about being clever in finding what data you need and making a convincing argument at the end of it. But ultimately, in terms of cost of use, your reusable option is actually slightly more energy intensive in terms of cost of use, but it's still very, very low because water and cleaning is not exactly the most environmentally damaging activity you could be doing. So given that we have to figure out how many uses we need to have data again to back it up. So by rejigging the formula you saw earlier, the life cycle analysis one, into a very kind of simple, and I would say very accessible type of concept for second level as well, if you wish to adapt even this particular material, feel free to do so. But this is a relatively simple way of looking at it. So how many uses does a reusable cup need in order to be a better option? Because we've already ascertained that in the production phase, a reusable cup actually takes a huge amount of energy compared to a disposable cup, primarily down to mass alone. And again, one way to think about that when you're designing is that we always design products with a particular number of uses or a life cycle in mind. Some items are designed to last for a very long time. Some items are designed to last for a very short amount of time. And that has a big impact on cost. The reason, often one of the main reasons, is not the only reason, that cheaper products break easier is because they have been designed to that limit, that budgetary limit. If they were allowed to select more expensive processes or more expensive materials, the item would last longer. So that's a concept called, sometimes referred to as planned redundancy. We'll talk about that again later on. It's not for now. But here we have a simple enough concept. Our break-even number of uses equals the energy of the reusable cup plus the energy of wash. So what that means is that as the reusable cup is used, let's say 70 or 80 times, we have to factor in all the energy that is used by the cup in that period of time to give a reasonable comparison, an accurate comparison. So that means we have to count in the energy of a wash. We have to figure that out somehow. And then we can divide that by the energy of the disposable, because the disposable doesn't have any use energy associated with it, i.e. it's used once and chucked out, it doesn't need to be washed. We can get quite a simple formula to give us a relatively simple answer, as long as we have the sometimes complicated data to start the comparison. Now, thankfully, you won't be required to make this comparison. I've gathered the data and I've presented a graph on the next slide. So using the formula that we talked about in the previous slide, we can now run some basic comparisons. And we'll see that I have to use my reusable ceramic cup. If we look very much on the left, I have to use that about 125 times before it is a better option than our polystyrene. But polystyrene isn't available in Ireland or Europe due to the environmental impacts we talked about previously for end of life, i.e. when it breaks down in a landfill, it's likely to blow away because it's so light, it's predominantly air, it'll get into water systems, cause a lot of damage. But if we were to use polystyrene, I'd have to use my cup, my reusable ceramic cup, 125 times before it would make more environmental sense. Now think about stacking up 125 disposable cups next to you. That's an awful lot of material. But again, think about how light they are. Think about how it's predominantly air in polystyrene. And that's where that comparison comes from. Now, if we have a look at our plastic coated paper and compare that, we'd have to use our ceramic cup about 10 times for it to be a better option than our paper cups. Now because that's a primary use in Ireland, I think that's a really, really interesting point, because that's only 10 cups. That's again, a coffee drinker having 1 cup a day conservatively in a takeaway cup. That's only 2 weeks worth of use. And the vast majority of us will be able to use a keep cup for a couple of years, you would hope. So the benefits over its use period of its life is huge, not to mention the other areas we explored in terms of biodiversity loss, the problem with man-made forests and stuff like that. And you'll notice as well, the break-even point for plastic coated with paper sleeve is slightly less than that, because as we add a paper sleeve to our, we'll call it an assembly of our paper cup, it adds more material. That means it takes more energy to make at the start a paper cup with a plastic top and a sleeve. That takes more energy, so the break-even point is a bit lower. Again, that's probably only 8 times. Now that's, again, less than 2 weeks worth of use for the ceramic. Now remember, ceramic, of all the reusable options, is very, very high in terms of its energy cost at the start. If we look then at something that's kind of middle of the ground, so reusable plastic. So reusable plastic is, again, one of the most popular types of reusable cups. But when we choose reusable plastics, we have to be careful about what we're choosing in terms of polymers and its end of life. So I told you before that PLA is not actually a good plastic to use for these type of cups. One of the reasons it's not good is because it has a relatively low hardness rating, i.e. it's a soft plastic. And also it's quite malleable at relatively low temperatures. So for those of you who have been messing around with 3D printing, PLA is actually one of the most popular types of plastics to print with. The reason it's the most popular is because it has quite a low melting point, which means it doesn't take a very heavy element, heating element in your 3D printer to print it up and print with it. So what type of plastics do we use? You could use high density polyethylene, which will be one of them. Again, you'll see the markings on the end. You'll be able to pick it out quite easily. But let's go back to the data we have here. In order to compare a reusable plastic, we would have to use a reusable plastic cup about 50 times. We'll call that 55 times to be comparable to polystyrene, so 55 times. But again, let's compare it now to paper, which is a bit more realistic in this country. We probably only have to use it about 5 times. So if you've got a reusable plastic cup, and if you use that 5 times in a week, or if you choose to get your takeaway coffee once a day, 5 times in a week in a takeaway cup, you've broke even. So every coffee you get in your takeaway cup or in your reusable cup after that, you're making a considerable benefit for the environment. So this at the moment now is only based again on use. We do need to consider production as part of this, but we're not really considering end of life in this comparison. That'll come later. Now, reusable and glass. So we'll focus here on reusable and glass, and we'll compare it directly to, again, our paper cup. That looks like only about 4 uses. So again, less than a week, you'll have your break-even point. Everything after that is a positive. So you use that reusable glass cup once a day for a year, you will have saved the environmental cost of producing it many, many times over in terms of its emissions. Again, this is a simple enough comparison, but it gets far more complicated when you have more complicated assemblies. Imagine trying to do this for something like a laptop, for example, where there are thousands of individual parts. It becomes a lot more complicated. But for now, this is a useful case study in exploring use and its impact on overall environmental impact. Okay, so I previously said that polystyrene is no longer allowed in Europe, and we need to talk about something in terms of data as well. So I've presented you now with some graphs, and it all looks very slick and professional, but I haven't actually given you any hard data yet. I haven't supplied you with a data source, either a data source that I've collected or a data source that I'm working from. And that is actually going to make up one of the key discussions at the end of this lecture. So we will get to that. But in the meantime, where am I taking my data from something as simple as polystyrene? What about its impacts? Am I just believing anybody on a blog on the internet? No. I'm looking for high quality reports from trusted institutions. So the following report there that I've popped up, just a snapshot of, if you Google IEEP Styrofoam or the Institute for European Environmental Policy, it will tell you about the impacts of polystyrene on water systems, on food cycles, and it will outline in considerable detail why it's not a very good material choice, especially for takeaway containers. So what I want you to do now, and I should qualify, I'm saying in pairs here, I have no problem with you engaging in peer or peer feedback or support networks if you have a WhatsApp group that you want to bounce this into and discuss your answers. But I do want you to consider and record each one of these questions. When I pose written questions like this, or when I hit on key concepts, you should be taking notes, because the quizzes that will come up after the first 4 lectures or 5 lectures will be touching on these topics. You'll need your notes for the open book exam to be able to score well on it. Okay, so consider the following 4 questions. Pause the video. When you've completed, unpause the video, and we will discuss the answers. I'm assuming you have now completed the questions and you haven't just cheated to skip through and see what my take and the answers were. If you have, fair enough. But remember that there are quizzes coming and you need to be able to be easily accessible in terms of your knowledge for this topic. So why is polystyrene such a useful material for food and drink containers? Uh, One of them is that because it is predominantly air, just surrounded by plastic, it's an excellent insulator. So for any of you who studied construction for Leaving Cert or have any experience in terms of construction, you'll know that polystyrene is one of the most popular insulating materials that we put in a cavity wall because it is incredibly good at stopping heat from flowing through it. Um, so that's one of the primary reasons. It's such a good insulator that you can hold boiling water with a very thin cup, a very thin sidewall, and you won't burn. You won't need a sleeve like you would on a cardboard cup. Um, but one of the other reasons why it's very useful is it is incredibly cheap to manufacture. You can make a polystyrene container for a fraction of what it would cost to make it from paper or more durable, longer living plastics. So using your phone to look up and report a quantifiable property of polystyrene related to its use in food containers. I've kind of given you a hint there in the first one. You should be looking for any quantifiable factor related to its insulation. So you can look up conductivity or thermal conductivity very easily, or typical insulation factors, or you could even look up something like density if you wished. You'll note that the density of polystyrene is very low, which means it's very easy to ship it because you can pick up a huge amount of it and move it very lightly. But primarily it would be some quantifiable property associated with thermal conductivity, i.e. how easily, or in this case really not easily, heat flows through a material. Okay, and number 3, identify and outline an environmental, economic, and social impact of widespread polystyrene use. And this is really important when we're considering material selection and environmental impact. There are many broad different types of impacts. So environmental, we actually talked about this previously. I would say one of the major concerns I would have with polystyrene use would be waterway pollution and microplastics ending up in water. If you've been to the beach lately, you will find an awful lot of polystyrene on the beach. An awful lot of it actually doesn't even come from this country. But once it gets into the water system, it will float all over the world. And if you want a really depressing picture of our current environmental health, you can Google garbage islands. So these are enormous areas of plastics as they form together in kind of a swirl pool in the Atlantic Ocean. There's actually other ones in other oceans as well. Again, there's loads of media out there on it. Have a look at it. In terms of economic, well, the economic impact to the producer is actually positive, i.e. it's cheaper for me as a maker of coffee cups to make polystyrene instead of paper. The environmental or the economic impact for local authorities is quite high. So beach cleanups all cost money, recycling initiatives and shipping all cost money, waste collection systems all cost money. So polystyrene use as a one-off container is, again, it does have high economic impacts for local authorities especially. And the social impact is related to that then. So if you go into a housing estate or a beach or a public park that's strewn with litter, that does have a social impact. It impacts community pride in their surroundings, and that has more complicated impacts in terms of how people treat that public space in future. You'll find that if a public space is allowed to be kept in a poor quality state, the amount of investment in terms of care and pride local people will give that space drops very quickly and will stay low for a very long time after it. So it does have considerable social impacts. I hope this gave you a brief overview of the many negative impacts associated with polystyrene. It in itself, used as a building insulation material, it's very good. It reduces heating costs in houses, and because it's secured in a wall, it will probably stay secured in that wall of a modern house for about 300 years. However, used in one-off containers, it's very poor. That again highlights the complicated nature of material selection for different tasks. I mentioned previously that polystyrene has excellent insulative properties or a low thermal conductivity. But again, it's fine to say that, but we have to back it up with numbers, and we have to be able to compare it to other materials. Otherwise, it's just better or worse. It's like saying that aluminium is a tough material relative to what? Is it tougher than lead? Is it tougher than iron? Does it have a higher tensile strength than lead or iron? One of those is true, one of those is not. So we need to have numbers to compare them, because engineering is based on decisions that are based on data. So when we talk about thermal conductivity, the easiest way to picture is how easily does heat flow through a piece of material? Now, in our example above, there's 3 hypothetical mugs that all have the exact same geometry. They all have the same thickness of sidewall. So I want you to picture holding that mug in your hand. Let's say you're camping, you're using a steel mug. When you pour boiling hot water into it, if you were to wrap your 2 hands around it to warm it, you would find you would quickly burn your hand, because a huge amount of the heat energy that's flowing from the boiling hot water is going through the steel and into your hands at a very, very high rate. That's because steel has a thermal conductivity of 14.3 watts per meter Kelvin. And that's, again, that unit defines energy flow as a function of distance and also as a function of thermal difference. As long as you understand the comparison, you can, in your own time, look up the derivation of the units. It's perhaps simpler just to conceive in the way we're talking about for now, i.e. you're holding the mug, how much heat energy is flowing out of your tea or your coffee into your hand, assuming it's at 100 degrees Celsius. So with steel, this high thermal conductivity relates to a relatively fast temperature equilibrium between the mug and the liquid, meaning the liquid will cool off rather quickly. What that means is that, and for any of you who've ever scalded a cup in order to stop your tea from cooling down too quickly, you might understand this. The first thing that happens when you pour boiling water into that cup is the heat energy will flow from the water into the steel until they're balanced. So what will happen is that the water will rapidly cool until the cup rapidly heats and they're in rough equilibrium. So if I was to pour 100 degree Celsius water into that, the cup would rapidly heat up, the liquid would rapidly cool down until they're at the same temperature. It'll probably settle out somewhere at about 80 degrees Celsius. And 80 degrees Celsius is too hot for you to hold. You'll burn your hands unless you're using the handle. And even the handle, because it's a good conductive material, will flow through and burn your hand eventually on that as well. So you can see there, it's steel, not a great choice. And your drink will also get cold quickly, which isn't ideal. Going back to scald your cup, if you were to scald the cup first, so if I was to heat up that cup using other boiling water, if the cup is already hot when I pour my cup of tea into it, it means that the rate at which my tea will cool has been reduced, because the cup is already hot, it doesn't want to draw any more heat off it. So it will come to a higher state of equilibrium. These are really important terms because while they're important for thermal conductivity, you'll see in a lot of material properties, it's all about comparison, and certain key terms like equilibrium and coefficient will come up again and again. On our second point there, the thermal conductivity of a ceramic mug is approximately 3.8 watts per meter Kelvin. Now, immediately compare that to your steel one above. This is a much, much better material choice in terms of insulation, in terms of keeping heat in the cup. The rate of heat flow from your liquid out through that cup is going to be a lot lower than your steel. So your tea will cool roughly 3 times as slowly. Now, that's not to say, on that factor alone, you would say that ceramic is a better mug than your steel. However, in a camping scenario, the reason you use steel mugs is because if a pack is dropped, or if you're climbing and you're bouncing off stuff, you need something to be very, very durable. So it's really important that your steel cup is very, very tough. But another reason why a steel cup can be used is that if you imagine a steel cup that has a very, very thin sidewall, if we make it as light as we can make a cup that will hold liquid that is lighter using steel than ceramic. And if I'm going to hike 100 kilometers, I want it to be as light as possible. Because remember, if we're going to make a ceramic mug, the sidewall has to be pretty thick because it's fragile, it's brittle. So here we're doing a very simple comparison based only on thermal conductivity, but know that there are a lot more complicated factors you have to include as well. Now, that's 3.8 watt per meter Kelvin in terms of the ceramic, and then the glass mug is only 1.1 watt per meter Kelvin. So the glass mug is actually the best in terms of keeping heat of our 3 examples there within our structure, purely based on thermal conductivity. But again, it's going to be way more brittle than the steel option. Now, finally, down the bottom, and this is why I was saying polystyrene is such a useful material, its thermal conductivity is only 0.03 watt per meter Kelvin. Now compare that above to steel. it is hundreds and hundreds of times better, thousands of times better at keeping heat from flowing through it compared to steel. And that's why it's used widely as an insulative material in houses. It's also why it's actually a really good container in terms of keeping heat in your food or in your liquid. Our problem with that material is ultimately its environmental impact at its end of life. So remember there again, many factors to consider. If you're only comparing one piece of data, you're only getting a small part of the picture. So again, with the paired questions, I won't enforce this, but I do suggest that you work with a group and that you bounce your questions and your answers over and back in order to clarify if you have any misconceptions. I would rather you not figure out you don't know something when it comes to an assessment. I'd like you to know that before you take the test so that we can give everyone A1s and have a fantastic time at the end of the year. Now, in this exercise, once again, I'm going to ask you to pause the lecture. I'm going to ask you to take some time, have a look at the diagrams above. They're again a way of communicating to you the principles of the question as well. And then I want you to consider the activity below. So if you could please pause the video now or pause the lecture, and in a couple of minutes come back and we will answer this. Okay, so let's consider first true conduction. Now, conduction is what we were talking about earlier in terms of heat loss for our previous example. We were only worried about conduction as in heat flowing through a material. So when two materials are in contact, conduction refers to how easily heat will flow through it. You'll also note that that is very similar in terms of electricity. Typically, what is a good thermal conductor is a good electrical conductor. So identify and explain a design consideration in travel cups that slows heat loss through 1, conduction, and 2, convection. We'll focus on that first one first. So the first one could be very simple. It could simply be material selection. If I choose a material that is better as an insulator or has a lower thermal conduction number on it, as we saw previously, that's one really simple way. I can just choose a different material that is better at insulating. That's one way of doing it. But often it's a bit more complicated. So one way, for example, that we make it even better at insulating in a modern plastic travel cup is that we actually create a vacuum. So we have 2 layers of plastic. They're bonded together, and then there's an air pocket in between, or even a vacuum. And because those 2 pieces of material aren't touching, so you've got your inner sleeve and your outer sleeve in terms of a keep cup, you'll note that the way heat can flow through it has been disrupted. Now, the easiest way to show this is in a double glazed window, where you'll find in the middle there's actually an air gap. So if you were to put your hand on one side and somebody else has put their hand on another, you couldn't feel any heat flowing through from one hand to another because of the air gap in the middle. It can't conduct through a vacuum. So that's one way of doing it. Whereas if you were to put your hand on one side of a single pane of glass and your friend was to put their hand on another, you would actually feel it heat up over the course of a couple of minutes. Now, glass is still a very good insulator, but it's not as good as if there's an air gap in the middle. So that's another way in terms of geometry and overall design that you could actually create a very efficient heat barrier. Now, you'll see that a lot in terms of the design of a flask. It's usually actually 2 layers with a vacuum in the middle. Now, in terms of convection. Now, convection is a bit simpler. So convection is actually a kind of a thermal flow. So whenever you have a body of liquid, if it's warmer at one part of it, it will cause it to flow, because as you heat up a liquid, it expands, so it wants to rise, and as it cools down, it wants to come back down. So even if you boil some soup, you'll see this happening the whole time. At the bottom, the soup will heat up and expand, and it will bubble up, and it will often draw, let's say, peas or carrots or any other fraction or piece of vegetables you've in up to the top, and it'll bubble back down to the bottom again. So that's a convection current. And I say current there, if a tidal current, if you think of it mixing around. But another way that happens, bar the liquid itself, is actually in the interaction of that liquid with the gas above it, the air. So there's a whole field of study called fluid dynamics, and it's how gases and airs flow over each other and together, and how different different systems interact. But here, a really simple example is if you put the lid on your pot, it'll boil a lot quicker. Now, why is that? Because an awful lot of the heat energy is escaping out of the pot, going through the top. But you might say, oh, but you just said that air is a very good insulator. And you're right, I did, and it is. But what's happening is actually convection is happening. So air is a very good blocker of conduction. It's very hard to get heat across an air barrier. But what's happening here is not that. As the water boils, the steam particles, as it converts to a gas, is flowing up and out. Now, steam at that instance is at 100 degrees. You're wasting a huge amount of heat energy as it flows out the top. If you seal that, or at least if you put a lid on top of it, you're keeping in an awful lot more energy. So the convection now is flowing up. As the water turns to steam, it's hitting the top of the lid, and it's actually keeping an awful lot of heat in it. And that we can see a similar design principle used in coffee cups, where some of them have a kind of a click over the drinking hole at the top. You can actually use a slider that would pop over it, or some type of a stop mechanism, and that will stop it. So a good example of a design consideration to reduce convection loss. So there we have a coffee cup design in terms of reducing loss of heat through conduction, but also reducing loss of heat through convection. Now, radiation we're not really bothered about, because water at 100 degrees does not radiate heat. If you want a good example of radiating heat, you would have to look at an electric bar heater. When it glows red and it radiates, you can actually feel the heat radiating across. That's a completely different form of heat transfer. We're not worried about that in terms of a coffee cup. If you are drinking something that is emitting heat through radiation, reconsider your dietary choices, because that's not going to be good for you in the short or long term. So all of that data so far and all of those comparisons and my clear obsession with coffee aside, we're now on to the last stage of your life cycle analysis, so post-use. So what happens when you're done using your product? Now, every product has a post-use. Even ones that are made to last 20 years, they will eventually not be used, so they must be disposed of. Now, how do we dispose something? Can we recycle it? Is recycling even a good option? And that's something that is becoming increasingly clear, that recycling actually isn't the type of fixing mechanism we think it is. Often recycling can be worse for the environment overall than using a modern incinerator, because while people don't like the ideas of incinerators, they recover a lot of heat from the mass of your object, and they can actually use that heat to power homes or to heat homes, or to recover the energy. And also you don't have to deal with the shipping problems, because we don't recycle widely in this country. But the very simple fact of the matter is that most materials do not recycle well. Paper can be recycled, but it gets worse with every time you recycle it, which doesn't exactly make it a great material for recycling. It's still better than plastics. The vast majority of plastics are really, really poor in terms of recyclability. So one of the examples would be if you take a clear plastic and you try to recycle it again, it will never be a clear plastic again. Its tensile strength will be lower. So often what you'll find is that recycled plastics are usually spun into a kind of fiber. So think about the type of fibers that make up your shopping bags or your tracksuits, nylon, stuff like that. That's where end-of-life plastic goes, either that or into a landfill, which is not good, because landfills, I don't think I need to explain, are a ticking time bomb in terms of environmental damage. Now, so let's go back to our topic at hand, our coffee cups. The main factor to consider in disposal is how often coffee cups are disposed of and how. Are they recyclable? What's the impact of recycling them, sending them to the landfill, or other outcomes? So in terms of disposable single use, the vast majority go to landfill. Now, they have to be transported to landfill as well. One of the reasons they are completely unsuitable in terms of recycling, and this is a big problem in UL, if you walk around to any recycling bin in UL, you'll find dozens and dozens of coffee cups in them, because the vast majority of people think that they're recyclable, and they're not. The reason they're not recyclable is that a paper coffee cup actually has a layer of plastic bonded to the inside of it to stop the coffee from seeping through the paper. So when you bond two things permanently like that together. So think back to permanent bonding systems, mechanical or thermal. It means that you can't expect a recycling worker to tear apart the inside layer of plastic and paper. It's not economically viable. So they have to go to landfill, uh, or in this case, they say that they're recycled. Now, what they're talking about there in that tiny sliver of recycling is that what can be recycled would be the sleeve in a coffee cup. So the additional sleeve you pop onto it, you can take that off and recycle it, or with the plastic lid can be taken off and recycled, although plastic lids are not recycled in this country. They're not widely recycled anywhere in Europe, to the best of my knowledge. And again, they're shipped to Asian countries, which often say they are being shipped for recycling, but more often than not, they're actually burnt in open fires, which is the most inefficient and environmentally damaging way of disposing of materials. So when we send our recycling abroad, even the little bit that is claimed to be done there, it is worse than incinerating it in a modern incinerating plant. A good example of a modern incinerating plant is one that was built in Dublin, and it faced constant planning objections because when people think of incinerations, they think of dirty black clouds of soot and ash falling down on top of them. So in terms of marketing, they changed the name. It was no longer an incineration site. Now it was an energy recovery recycling plant. Now what that means is they burn the product and they recover the energy from it, and they use that energy then to either generate electricity in this instance, or sometimes they use it for broad heating requirements. And because a modern electricity plant has really complicated exhaust systems like you'd find in a modern car, it scrubs out the vast majority of the harmful particles coming out the top. Incineration is empirically, data supports this, studies support this, a better option for end-of-life plastics than sending it to multiple Asian big contractors who tend to not actually recycle them properly or responsibly, and instead damage local environments and communities. So all of that being said, and all the poor practices in terms of recycling that happen, what is the actual cost of disposing of a single-use cup? Where's the cost coming from? So it's difficult to calculate the cost of disposing single-use cups because of various scenarios. What we mean by that is that different people will dispose of them differently. So some will chuck them straight in the general waste bin, some will chuck them straight on the ground, some will pop them in the recycling bin, even though they shouldn't. So there's a lot of different ways with that. So over the course of the next 6 minutes, I'd like you to pause the video and I'd like you to create a list of all environmental impacts associated with the disposal of a cup. Again, think broader, bigger picture now that we talked about earlier. You've got social impacts, environmental impacts, and economic impacts. So please pause, do your best in terms of coming up with six or with a couple of options over the next 6 minutes, and then we will go over my options or my list that might be different but should be comparable to yours. Okay, so once again, trusting that you haven't skipped straight through, because again, I need you to be familiar with these concepts and I need you to engage to the best of your ability with this material. So let's have a look at a couple of ones I came up with. So collecting and transporting used cups is energy intensive. What I mean by that is that requires transporting from individual collection points and bins, and then we have to collect those using trucks. Trucks are relatively inefficient in terms of transport compared to rail or sea, and they will emit quite a lot in terms of energy just gathering up all these coffee cups. Once in a landfill, cups may break down slowly in the right conditions, but their plastics will take hundreds of years, resulting in landfills that are wastelands. So landfills that are used in this way will be a constant environmental risk waiting to break down. So one of the examples, there's a landfill in Youghal, and it's placed right next to the sea. The problem with that is that they've invested many, many millions to try and line the entire landfill with a thick layer of plastic to stop all the water flowing out of the landfill. Because as water flows through plastic waste, it picks up some water-soluble compounds and some small plastic fragments, and it then flows directly into the sea, which is why building a landfill next to the sea is one of the stupidest public planning decisions you could ever come across. and it's done in Youghal. Another issue is that water that's flowing out is called leachate. It's kind of a soup of plastic molecules mixed in water, and that has really, really bad impacts in terms of wildlife and the local environment as well. Another problem is greenhouse gas release from landfills is a major contributor to global warming. So as all these pieces of matter break down, they will release gases. And because landfills can generate quite high temperatures, you can end up with different types of breakdowns. So those of you from a farming background, you may be familiar with the term aerobic and anaerobic digesters. There are different ways of breaking down materials, but it basically means that if a material breaks down in the presence of oxygen, it will break down in a different way and produce methane. Which is a seriously potent global warming gas or climate gas. If it breaks down in anaerobic, i.e. without oxygen, it produces different types of gases which are also harmful. So greenhouse gas emissions from landfill is a major, major problem. Cups that don't make it to landfills pollute the natural environment. Simply look out your window as you go for a drive the next day, or if you're in an urban environment now, even just go for a quick walk. Within 100 meters, it's likely you'll find some part of a coffee cup strewn somewhere. And that is a source of pollution. It's also just unsightly. Incinerating disposable waste will recoup some of the energy, but also results in emissions that contribute to global warming and air pollution. So while incinerating is a better option, it's still not a good option. It still results in global warming and air pollution, although the most modern, efficient incinerators are very, very good at drawing a lot of energy compared to simply leaving it in landfill or compared to inefficient recycling practices. The sheer volume of disposable cups thrown away on a daily basis is hard to fathom. Starbucks alone produces 4 billion each year. And that's, again, just trying to think about that for a second. If we consider the global population as being almost 8 billion at the moment, Starbucks as one company is producing enough paper cups that every second person in the entire world could have one, obviously in the year. So what about every other coffee house, every other little shop? And again, you might think it's strange that I'm focusing on coffee cups only. These are not the biggest environmental challenges, but it is just an example of the absolute scale of the challenge ahead of us. Indeed, if you thought that this was a quite, let's say, oversimplistic or even ridiculous example to take, in a way, you're right. An even more ridiculous example is McDonald's moving to plastic straws from paper straws. It was seen as one of the greatest wins for the environmental lobby in recent years. And in terms of all plastics used and damaged by plastics, it means nothing. It is such an infinitesimally small fraction of the problem that it just doesn't matter. And yet it was celebrated as if we'd won something major. And in that way, that type of advocacy is actually damaging. Thinking that that's a win is like thinking that, okay, my house is on fire, but I did plug out the TV, so I am saving some energy. It doesn't matter if your house is on fire, how many appliances you plug out and save energy on. It's just not comparable in terms of concerns. So when you make small adjustments to your own purchasing, that will have an impact. And as a general population moves towards better practices, that will have a big impact. But one supplier making one small change and then using it as something in terms of PR and marketing for the next couple of years, it's a very dangerous way to look at a bigger problem. So once again, if the house is on fire, you don't concern yourself with plugging out appliances. You find a necessary emergency large-scale action to tackle the severity of the problem. So how do all our options stack up when we compare them for end of life? You might have noticed that ceramic is not coming out too well across this. It takes way more energy in its start use, and it is actually often more brittle than tempered glass. It also has poorer thermal conductivity than tempered glass. So ceramic, while it can be stylish in terms of it looks very nice, and from a marketing point of view, it's pretty cool, it's actually a poor material choice for this type of application. Your more modern keep cups that are made from glass are much, much better for a number of reasons. Ceramic is very poor in terms of recyclability because ceramic is actually a layer of different materials. If you break a ceramic cup, you'll find often that the outside layer is kind of an enamel glass and the inside is a different type of ceramic. And ceramic can't really be recycled. You can't heat it up again and get it to melt down as such. It doesn't really work like that. Plastic alternatives can be recycled and will last for thousands of times. So I really should have a little asterisk there. Certain types of plastics can be recycled and they can be used for different uses, like let's say fibers in clothing or in bags, but they're not a great type of recycling. But as an option, if you're going to use it enough times, they're very durable, they're very light, they've got good insulation properties. A reusable plastic cup is actually also a very good option, much better than ceramic. And then glass cups. These can be recycled. Glass can be recycled quite well. So while clear glass can never again be clear glass, it can be reused in terms of green or brown glass for, let's say, different recycling of different containers. I'm sure you're all very familiar to different glass containers that are used. And then glass cups as well, because they are, again, clear, they can be reused in wider stock. But if you get tempered glass, which has very good toughness, not as tough as some comparable plastics, but tempered glass has good toughness. It won't shatter very easily. It has very good insulative properties. And overall, it's objectively one of the better options out there at the moment. But you still will, even then, you'll have to pair a glass cup with a plastic top. And usually that you'll see them now with an additional cork-based natural product grip, which again, cork is a very good insulator. It's a very environmentally friendly product, as opposed to the material is actually quite good. So those are the general stacking up, if you pardon the pun, of reusable cups. Now, so throughout this, I threw a lot of data at you. And again, the first thing you should be asking is, the person is talking to me or telling me something. Do I trust them? So is the data they're presenting likely to be accurate? And that is an important question to ask. If it was just some person with a blog on the internet with no reference sources, you should be very, very wary. Even with me, as an academic, I might have huge biases towards certain types of products or certain types of manufacturers. And again, you shouldn't be basing your conclusions solely on what somebody told you to think. That is never a good way to be a consumer or a designer. And if you believe something to be inaccurate, look into it, find the data and see if it is inaccurate. It's really, really important. So for example, my top source there, one of the first sources I found was a web page from Turn Goods. So single use versus reusable, an honest comparison. Now, it was a very, very very simple argument, and actually showed that disposables were definitely the better option for 99% of consumers, and that's what I should be using for my business needs in future. Unfortunately, Turn Goods are one of the largest manufacturers in the US of disposable cups, and to the best of my knowledge, they don't make any reusable products at all. So, do I trust that web page? Do I trust that company as an information source? No, I'm not going to. It's like when Shell or BP tells you that fossil fuels are actually, they're not that bad at all. In fact, they're pretty good. Their entire revenue stream comes from oil. They're of course going to defend it. If you look back to when cigarettes were being banned in the 50s and 60s and 70s, the tobacco lobby was able to find a lot of really poor quality scientists that would say that not only does smoking not give you cancer, it actually helps protect your lungs. It's nonsense. So you should be looking at the biases of the person presenting the data, as well as how reliable that the platform on which it's published is. So a peer-reviewed scientific journal, for example, is a much more reputable source than a blog or a web page, because in order for a scientific paper to be published, it has to be reviewed by independent scientists, and it's also publicly challengeable by anybody. So if you find a major glaring irregularity in one of my academic papers or in one of the ones I've said here, you can actually write to the editor and say, this paper is inaccurate, its conclusions are flawed, it should be retracted, and that means it's taken out of the record, which is a really important part about modern science. So back to the sources that I use. A lot of the data that I use today came from a study in 1991. Its source is Science, a journal, a new series journal. And that was a very good study presented on paper versus polystyrene. The comparisons were quite simple, but as we found out today, a lot of the decisions are actually different depending on how it's going to be used, and also where it's going to be used and at what stage of its life cycle. So a complex choice is the title, a very, very apt title. Now, the second paper I based it on was a paper in 1992, reusable and disposable cups, an energy-based evaluation. And that was where all the energy figures that we took came from. Again, an excellent paper written very well. However, a couple of things to caution. Both of these papers were written by the same author, means the same researcher. My chance of biases have increased here. If I had multiple different researchers from different countries and different research groups all reaching the same conclusions, I would be more sure of how much I could trust it. Although these papers are widely sourced by a lot more recent papers, and they're seen to be very, very good examples. Now, another thing might concern you, and you might have heard this a small bit in academic writing. Oh, your references should be modern. They should be no more than 5 or 10 years old. I agree with that in certain systems. So if we were talking about lithium-ion battery production, the way we make batteries has changed so much in the last 10 years that if I was looking at their environmental impact, my paper should be very new. Even in the last 3 years, we've made major strides. However, how we make paper and plastic cups has not changed since 92 at all. Our processes are the same, our materials are the same, there has been no major advancement. So I'm perfectly happy to use a reference that is from 91 or 92, which is more than likely a decade before most of you were born, if not more. So what have we learned today? I suppose to start that I probably have an unhealthy obsession with coffee. But going a bit further, it's that when we consider the environmental impact of an item or product, we have to consider the full life cycle. So again, life cycle analysis is considering everything from production to use to end of life. And that is a really complicated concept. At face value, it looks quite simple, but as we drill more into this, into the different decisions that we have to make, we'll find that very, very simple decisions like using an adhesive instead of a screw, for example, to secure two parts together has huge impacts for recycling at the end of life because it's very hard to separate something that's been glued. But the main thing I'd like you to take from that point is that you need to have a good general understanding of these decisions and their impacts. The second of that was, and it's actually presented in one of the titles of the papers that I used as the basis for this lecture, is that it's a complex choice. In different scenarios, in different use patterns, what can be good is sometimes bad, what's bad is sometimes good. We can only base it on data. So we can't just say that one thing is good or one thing is bad. And we actually saw an example of our own university marketing a reusable cup that was poorly designed and poorly produced. And the vast majority of those reusable cups that were produced, and I believe there was many thousands of them produced, I think enough for every staff member and student at the time. The vast majority of those reusable cups now, 2.5 years later, are probably in landfill. They're definitely not being used at the same rate that they should have been because it was a poor choice. But finally, and this is perhaps most important, in engineering, decisions have to be made on data. So when you make a decision, you have to be able to defend it. Now, I might disagree with you in terms of what material you chose, but if you have a good reason for using it, you might not be wrong. Your value system might be different. So maybe your decision was based on, I need to reduce the cost of my cup as much as possible to make it an economic success. Fair enough. Or maybe you want to make the best possible long-lasting cup. Again, different outcome in terms of your design, different priorities. So you'll make decisions based on that. But if you're not basing your decisions on data, you're simply going on gut instinct. And that's very dangerous. We're seeing that at the moment in terms of what that means for democracies around the world, where people believe something more than they care about its actual objective truth. So just because you like an idea or just because you think something is good doesn't mean it necessarily is. You have to look at the numbers and the data behind it. And I'll even go one step further. Just because I'm telling you something is right does not mean it necessarily is. You should be able to interrogate the ideas that I put forward in my lectures. And in instances where you find a weakness or a flaw in my logic, or even just an error in my work, you should be willing to come to me and say, hi, Jason, you made a miscalculation there, so your conclusion is flawed, or the paper you're actually basing your conclusion on is weak as well. It's been retracted since. You need to rethink that. And that's a big part of being a researcher. It's a big part of being a teacher. And I would say it's probably the most important part about being an engineer, knowing when you have made a decision that is incorrect and being able to substitute in something that is better instead of it. Okay, that's it for today. We will be drilling down into these concepts a lot more in the coming semester and a lot more in your next year. So please, if you are struggling with any particular concept now, take the time to read up into it and come to grips with it. I don't want you to be struggling later on in the semester. Thank you for your time.